Hello students, in this video let us discuss decarboxylation. So mainly I focus on the stereochemistry of the decarboxylation. So here the decarboxylation of mainly beta keto acids and dicarboxylic acids. These beta keto acids and dicarboxylic acids on just heating, removal of CO2 takes place, nothing but decarboxylation. Okay. So first of all, briefly we will discuss the mechanism of the decarboxylation. So first of all here beta keto acids. Beta keto acids. So here RC double bond O CH2 C double bond OH. So this one on heating we will get the RC double bond O and CH3 plus CO2. So here generally by heating of the beta keto acids here decarboxylation takes place through the cyclic transition state. That means in this cyclic transition state there is a migration of the electrons takes place. That means here alkyl group, here C double bond O, here CH2, C oxygen and hydrogen double bond. So totally we can see this is a 6-membered ring. 1, 2, 3, 4, 5, 6. So here transfer these electrons to the oxygen. So this one negatively charged oxygen, so attracted towards positively charged hydrogen, and these electrons transfer to this one. And here this carbon-carbon bond breaking takes place. So there is a pi bond formation between these two carbons. So here finally this decarboxylation takes place through the enol actually. Okay. Plus here C double bond O and C double bond. It's a decarboxylation reaction. Now this enol is converted to ketone. That means here the proton is transferred to this carbon is nothing but 1 2 3 transfer. Okay, that means 1 3 shift of the proton. So here that enol is converted to keto form. So here the intermediate product is you can say enol. Okay, this decarboxylation takes place through the enol form. Okay, so here enol about this C double bond C geometry is planar. Okay, that's it. Now there are the beta keto acids. So here in this beta keto acids decarboxylation, here enol is the reaction that means one of the intermediate product. So here now this bridged carboxylic acid on heating no reaction. Why? Because in this case double bond formation at the bridge head carbon is not possible. That is known as a Brett's rule. That is known as actually Brett's rule. So at bridge head position sp2, that means the planarity is not exist. So here this compound is not decarboxylated. So here beta keto acids are decarboxylated. So now here we'll discuss one example that beta keto acid. Here in this case this example you can see it is an interesting example. So here in this one CH3CO CH2C double bond O and here D. So here in this case the reaction intermediate is the enol. This is the enol reaction intermediate. So now here this enol converted to keto form. So in this keto form here we will get the deuterated compound actually. Okay. So finally that compound contains deuterium. So now here the one more example. For suppose this is the compound PHC double bond O. Here in this case CH3 and deuterium. This is the beta keto acid on heating. What is the product? So here the reaction intermediate product is enol actually. That means here deuterium and here CH3. So it is enantiomerically pure compound this is. Okay, enantiomerically pure compound. That means here this is an optically active compound. It is actually a single compound. It is a single stereoisomer. That means enantiomerically pure compound. Of course, another enantiomer is possible. In that enantiomer, that methyl may be above the plane and deuterium above, that methyl below the plane, deuterium above the plane. Okay, so here in this case, this compound on heating will get the enol and then we'll get the product, that is a ketone. So now here that pure enantiomer pure compound, that is optically active compound, converted to optically inactive compound, this is. Okay, so now here this optically inactive means here about the C double bond C, it has a planar geometry. Now here this planar compound again converted into ketone. Okay, that means here C double bond O, here carbon, and here deuterium, hydrogen and CH3. That 1,3 shift of the proton takes place. Okay, so in this case again here one chiral carbon is generated. So now we started with enantiomerically pure compound. We will get the optically inactive enol. There is a planar. Now it is converted to ketone actually. That enol is unstable thermodynamically. The ketone form is thermodynamically more stable. So now here in this conversion, at this carbon configuration may be R or S configuration. That means here we will get the finally C double bond O, here C, here in this case hydrogen, that is right on the plane. Next here above the plane methyl, below the plane deuterium, or PHC double bond O, here hydrogen, this one CH3 or deuterium. Okay, so here in this case here mixture of two products are obtained because it is a planar one, so that has a equal chance to convert into these two isomers. These two are the enantiomers, so we will get the racemic mixture in this decarboxylation reaction of the particular reactant. Okay, so it is one of the important example. And next, for suppose see this compound, your COOH, and here in this case CH3, this is the double bond O. Now this one on heating, it is again beta keto acids, alpha beta. This beta keto acid on heating will get the this compound. Okay, now here CH3, that is the enol form. So now this enol form converted into keto form. In this keto form, C double bond O and one form, and here also C double bond O. But here this methyl on the plane actually. This is sp2 carbon, so methyl on the plane. But whenever it is converted into keto form, that methyl may be above the plane or methyl may be below the plane. That means we will get the racemic mixture. Okay. So here 50% of this isomer and 50% of this isomer, both are enantiomers, will get the racemic mixture. So but here in this case, this isomer enantiomerically pure compound. Okay, and what is the configuration of this chiral carbon? Here in this case, this one the first priority group and this second priority group, this is third priority group. So 1, 2, 3 are configuration. So enantiomerically pure compound this is. So if you start with enantiomerically pure compound, after decarboxylation we will get the racemic mixture product. Okay, because of the this planar enol compound. Okay, so it is about the decarboxylation of the beta keto acids. Now 1,1-dicarboxylic acids also decarboxylate. Okay, so that means here CH3, this one CH2, C double bond OH and C double bond OH. Okay, the CH. So here this one on heating. So this carboxylic acid groups both are attached to the same carbon. In this case, on heating decarboxylation takes place. CH3, CH2, C double bond OH plus CO2. Okay. Now, how this reaction takes place? Again here, the similar fashion as in the case of beta keto acids. So here in this case OH, here double bond O, here C double bond O and OH. So here in this case, again here the migration of the electron takes place. These electrons transfer to this one, and this negatively charged oxygen attracted towards H plus, and then here the breaking of this carbon-carbon bond, here pi bond formation. So here finally we'll get the CH3C H double bond, here OH, and this one is OH. So again it is a enol form. Now this enol form converted into keto form by the proton transfer. So CH3C H2 COH and double bond. This is a carboxylic acid. So again here in this case that is a enol. So it is a planar enol. This planar enol may be converted into that non-planar actually. So here if you start with one carboxylic acid, that means here I am starting with this carboxylic acid. So here in this case I'm writing like this COOH, here COOH, and this is CH3 and ethyl. So here in this case, this one on heating, what is the reaction intermediate product? So here actually that is converted to enol. So CH3, and this is carbon, and this is ethyl. Okay. So now here what is the enol actually? This carbon double bond, here OH, and this is OH. Now here again it is converted to that carboxylic acid, C double bond O, and CH, here CH3, and this is ether. Actually here about this carbon here no stereochemistry actually, because it is the sp2 carbon. Now this sp2 carbon converted to sp3. Okay, in this case that maybe has R configuration, or maybe it has a S configuration. That means here there is a possibility of the two isomers, because whenever one planar compound convert into non-planar, that maybe here groups can be changed. In one case that one group above the plane, or in another case that group, the same group exactly below the plane. Okay, so here in this case, in this decarboxylation, we will get the two isomers. For suppose COOH and here hydrogen and ethyl, plus or COOH. So actually here in this case, COOH and here hydrogen and this CH3 ethyl. Okay, these two are the actually enantiomers. Whenever this compound on decarboxylation, you will get the racemic mixture of products. Okay, because here either group, that means here through the enol actually. Okay, this reaction takes place through the enol. That enol may be converted to either isomer actually. Okay, so we'll get the racemic mixture. So we can say here in this case it is a prochiral carbon. Prochiral carbon. The prochiral carbon means here that is ready to change into chiral carbon. So after decarboxylation, this is the achiral carbon converted to chiral carbon. That is a prochiral carbon. Okay, it is a one example. For suppose, let us discuss one more example that's regarding this stereochemistry of the decarboxylation. Okay, so here the CH3 and this is ethyl. This one is the deuterium and the hydrogen. Now here COOH and COH. So this one on decarboxylation, here CH3 ethyl deuterium hydrogen, here hydrogen COH. Through the enol form add this carbon, either form is possible. That means yes, maybe COH comes to the right side or COH comes to the left side. That is hydrogen deuterium hydrogen, here ethyl and CH. The relation is diastereomers, because these two are the non-mirror images, so diastereomers are possible, because here this chiral carbon configuration is fixed. Okay, that's it. So here you can say in this case diastereotopic hydrogen disease. Okay, now here let us discuss this example. Here this is a methyl and this is methyl. Okay, So here this is a COOH and here this COOH. Okay, so now here this is converted into enol form. Okay, that means here CH3, here CH3. So enol form means here carbon OH, here OH actually. That is the enol form. Now this enol form converted into that non-planar compound. Okay, about this carbon there is a planarity. Now it is converted to, that means here proton transfer. Okay, so in this case that proton may be above the plane, so COOH below the plane, or the proton may be below the plane and COOH above the plane. So here what is the relation between these two? These two are the non-mirror images, again diastereomers. Okay, and this compound is optically inactive compound. This compound is also optically inactive compound due to presence of the plane of symmetry. So it is a meso compound. Here also it is a meso compound. Okay, but the relation between these two are the diastereomers, because in this case all groups in cis position, but in this case all groups are not in cis position. Of course these two groups are cis position, that means same side, but a COH opposite side, that is a below the plane. Okay, so here one more example. For suppose here this one CH3 and hydrogen, here CH3 hydrogen, this is COOH and COH. Okay, that means here in this case here almost these two are same. So this one heating, so here we'll get the again the same meso type of compound. So here in this case CH3 and CH3 hydrogen, this hydrogen, here hydrogen and COH, or this is CH3 and CH3 hydrogen hydrogen, this is COOH and hydrogen. So here actually here there is a plane of symmetry, here there is a plane of symmetry. So it is a meso compound and it is also meso compound actually. Okay, so the relation between these two are the diastereomers. So this is the possibility of the formation of the products in a decarboxylation reaction. Okay, so that is about the decarboxylation reaction and stereochemistry. For suppose in this case let us discuss one more example. Here the COOH and here COH. Okay, this compound on heating, what is the product? Actually it is a 1,2 dicarboxylic acid. It is not a 1,1 dicarboxylic acid. So here this dicarboxylic acid on heating, dehydration, that means here anhydride is produced. So removal of the water molecule, so we'll get the cyclic anhydride. Okay, so that is about the decarboxylation reactions. So thank you for watching.